Welcome back to the classroom. My name is Mr. Wong. Today we'll be looking at a new module for HSC Physics. This is Module 6, Electromagnetism. As you can see, we have a couple of inquiry questions, 4 in total. And in the one we're focusing on, it's how charged particles and conductors behave in electric and magnetic fields. These are the dot points we'll cover today. Okay, so our lesson intention is to investigate the interactions between charged particles and those of uniform electric field, and we're going to try and derive some relationships from this. Before we start, remember the current topic, electromagnetism, is actually one of the 4 fundamental forces that exist in nature. So we have the electromagnetic force that presides with electrostatic force, magnetic force. In Module 5, we talked about gravitational force. And then there is also the weak and the strong force. But they don't come in until a couple of modules later. Okay, so the question we need to firstly ask is, what are non-contact forces? A common description that we use is forces that occur without the need of physical contact. Well, scientifically speaking, or using the correct words of explanation, it's when a force is facilitated or mediated by a field. So say if we have 2 electric charges, the positive charge will want to move towards the negative charge, and so it experiences a force of attraction. At the same time, it also experiences a force of repulsion from this positive charge here. So that's what we see here. So that's what we see with magnetic fields as well. Same idea. Just a quick recap. What we mean by a field is in reference where there is a region of space that has a specific value. So it could be a temperature field, it could be air pressure. In this case, what we have here is an electric field, and as you can see, it has a specific potential. So that's where any region where a force can be applied to a specific object that we are trying to observe. Okay, and so we get to our very first dot point that we have here, which basically states the uniform electric field. Okay, what we're going to be investigating is electric field between parallel charged plates, because this question is actually asking, analyze the interaction between charged particles and a uniform electric field. What we mean by uniform electric field is that we have the same electric field strength. So we're looking at scenarios with these charged plates here. As you can see how the lines are evenly spread apart to represent that we have an even field strength. Whilst if we look at the 2 charged particles here, you can see the density of these fields do alternate a little bit. So what that would mean is the electric field strength here is much stronger than the electric field strength over here. Okay, so that's what we're going to look at. And then we're going to look at a concept of acceleration of charged particles in an electric field. But before we do, have a multiple choice question for you to look into. Which of the following diagram correctly shows the electric field between a point charge or point charges or the charged particles? I'll give you 3 seconds. 1, 2, 3. Okay, so the answer for this is D. Okay, so the electric field's going towards the negative charge. Just remember, when it comes to the motion of electric fields, it always goes from the positive charge towards the negative charge. So what you can see in the first one, we go negative to positive, that's incorrect. The field lines are going to both positive charges, again incorrect, and C is actually just the same thing as A, so that's also incorrect. Okay, so now we're looking into what we call a uniform electric field, that is the charge plates. Okay, so over here, where it's positive, we call this the location of a higher potential. So where the positive part of the plate is, we say it's high potential. high pot, and then, or high 10, poten, and then on the negative charge plate, we call it the low potential location. It's just how they originally defined electricity, going from high potential to low potential. So that's actually how they originally came up with the idea. They're separated by a particular distance, which we labeled as d. And obviously, if this side has one potential and this side has a different potential, we get delta V, which is the potential difference, or what we also call the voltage of the two plates. If we add those together, we get the electric field strength. The electric field strength is defined as delta V over D. This is something we looked at in Module 4 to account for the electric field strength of a charged plate. Just remember, this only applies to a charged plate, doesn't apply for two charged particles. The distance of the lines are relatively even, which means that the electric field strength inside the plate is also the same. The only part where it's different is on the outer edges that we have here. That's the only spots where the strength would be different. Okay, now what we want to show is how charged particles interact in an electric field. So what we have is we know that the electric field strength is constant. Hence, if there is a force applied, it would also have to be constant. The reason being is we talked about force equals to charge times electric field strength. So for a charged plate, if E is constant and the charged particle is constant, because if you fire an electron, the electron only has the same amount of charge anyways, then the force applied to our charged particle is also constant. So that's constant, and this is also constant. Okay. What else could that mean about the acceleration? So clearly you can see that we have a directional change. The original motion of our charged particle was to go straight across. But we can see that there is a directional change where it's going in this direction, right? And as a matter of fact, our motion actually looks like a semi-parabola, okay? Now, if you remember what we talked about with projectile motion, this essentially looks like a projectile in motion, meaning by there is a horizontal component and there is a vertical component that we see here. Okay, so now we know that there is a directional change. If there is a directional change, that means there must be some kind of acceleration, which can also be applied because there is a force being applied to it. Okay. The acceleration will also be constant because the force that's being applied on it is constant, and also the mass of the particle doesn't change. Okay, so what we can actually do is we can find the acceleration of a charged particle in an electric field by equating equation 1 and equation 2 together. So it will be Q E equals to M times A. To make A the subject, it becomes A equals to Q E over M. And that's the equation we can be using to express the acceleration of a particle in an electric field. And that is a constant electric field strength. Go through it again here. So if we have a particle that interacts with a uniform field, we get the formula up here to express it. That also means with a constant force, we also get a constant acceleration. And that leads us to the charge particle formula acceleration here. Okay, that's what we have. Okay, next bit here is obviously just revising through some old equations. So one of the old equations we talk about is the electric field strength over delta V, or delta V over D. So that's just to represent the electric field strength that we have here. You might have noticed a negative sign. That's just to introduce the E field is always moving from a higher potential towards a lower potential. Okay. Um, but in the grand scheme of things, you don't really have to worry about this negative sign here. This is just the formula we want to represent. Sometimes you might actually find that the formula can be written like this. It probably is written like this on your data sheet, potentially. Let me just check. Yep, so it's written like that on your data sheet, but the technical um, way of writing it should be delta V over D, because this V represents electric potential, which would imply the field strength at that particular point, which obviously it's not that easy to find the actual potential at a particular point. We also defined what potential difference was. We said that potential difference is the amount of energy, or the amount of energy to, let's say we have a charged particle, to move it from this point here to this point here. Okay. To move an object from one spot to another, we obviously mean it's work. Okay, so the amount of work done is equal to the change in potential energy, or it could be the change in kinetic energy, because you can go from stationary, or you could be moving, and then you make it move into a particular direction. Okay, so what we can try and do is demonstrate a relationship between potential difference and kinetic energy, and also potential energy as well, and work done. So let's have a look. Okay, so now we're looking at trying to derive the work done formula. If we have a charged particle and we move it along an electric field, how could we express that? Now, the force applied to a charged particle is given by this one here. Again, remember, the E of this formula represents that we are dealing with a uniform electric field. So we're not looking at examples where electric field changes, we're just looking at if it stays the same. If we're looking at that, so if we move an object from one position to another, okay, and that position is in the same parallel direction as the force applied, as you can see with this diagram here, then we can express it as work done. Remember, work is only completed if you move the object from one position to another, and if the force you apply is in the same parallel direction as the motion that you're witnessing. So if we substitute the formula that we have here with this formula we have down here, it becomes EQS. Okay, S being the distance of motion from one position to another. Now, in the formula sheet, it's usually represented as this. So EQD, D meaning the same thing as S. They're sort of interchangeable. It's just the distance between that's been moved for the charged particle. But we can actually go a little bit more. So here we've defined the work done. So that's work done for a charged particle in an electric field. But we can actually go a bit further to find a relationship of the potential difference between one point and another where the charged particle is. So say this is the electric field. This is the original potential. So that's how much electric potential we have here. And down here, this is our new electric potential as the particle goes from here to here. Well, we can actually find that using the following formula. We know that potential difference is work done over the charge of the particle. So what we have here, if I simply rearrange Q over to W, W over Q equals to E times D, that becomes the formula we use to represent the potential difference or voltage to move a charge between an electric field. So here's a relationship. So we have this one here. We have this relationship here. Again, let's just check with our data sheet to see if they are all in this equation. And as you can see, that is also in our equation here. We could also redefine the formula for work done as work done is equal to delta V times Q. So we can use this formula here to represent work done, or we can use this formula here to represent work done. So you can see how you can move these formulas around to express different components. Okay, so that's the formula for electric field strength. We've talked about it before. And these are all the formulas. So we have the electric field strength, we have the force experienced by a charged particle in a uniform electric field, and then we have the acceleration experienced by the particle. And obviously, don't forget, we also have the work being done. Okay, so there's that. We might go into some questions in a separate video, but this is how you would derive the equations for electric field strength, force, acceleration, and also work done, which is not on this one, so we'll go to that one. Okay, so we're moving back on to work done. So we already derived a formula for work done, but let's just show it again, or show it in this section here. Okay, so what we just quickly mentioned, we did the derivations. We got this function here. What we do know is if you're making an object move from one position to another, so from here to maybe here, obviously that motion equates to an increase in kinetic energy. Another way of putting it is, as we talked about before, at this position here, they had some form of electric potential. And if we move the charge down here, it's got a change in potential energy. Now, if this is the higher potential and this is the lower potential, technically, if we've gone from here to here, we have a decrease in potential energy of the electric field, right? So this is a relationship we can write like so. So we can say that the work done to move a charged particle from one position of the field to another is actually a loss in potential energy because the electric field is the electric field is doing the work to move the charge down here. So that's why it's a negative, but the charge itself is gaining kinetic energy because it's moving along like so. Okay, so that's quite a few formulas that we've already looked into, as you can see from these ones here. And like we said, with a little bit of manipulation of the formula, work done can be expressed as EQD, or it can be expressed as the work times potential difference times the charge of the particle. At the same time, it also means a loss in potential energy, okay, or a gain in kinetic energy. Okay, so we'll just wipe that out. So we get that. Okay. Now, kinetic energy is an interesting one. If we have a charged particle so we know the change in kinetic energy is half mv final minus half mv initial square, we can find the velocity of the moving charge. Under certain circumstances, your charge might not be moving originally. So if it wasn't originally moving, or if it was originally at rest, we can express the formula like so. So if it's at rest, that means Vi originally was 0. So if this is 0, we get half mv final square. So we can express the change in kinetic energy this way as well. Okay, on the next slide, we also express the same idea to show this relationship here. Okay, just remember, if we are moving the charged particle from the high potential end to the low potential end, so we go from high to low, we are losing potential energy. So losing potential energy. Okay, so that's what we have here. Obviously, if we have a negative charge that's moving in the opposite direction, also the same idea. We're losing potential energy in that case as well. Okay. All right, so that ends today's lesson about how charged particles behave in electric fields. We talked about how to derive a formula for electric field strength. We looked at how to find the force on the charge. We also looked at how to find the acceleration a charged particle experiences on an electric field. We also stated that the motion of an electric field or the motion of a charged particle in an electric field looks like a semi-parabola. So it's parabolic in its shape, which is similar to a mass object in a gravitational field. Keep that in mind, that because we're going to go back to this concept later on. And we also talked about the change in kinetic energy is equal to the work done, which can be expressed in the following formulas, and so on and so on. Okay? If any work is done by the electric field, then it means that we're losing potential energy and gaining kinetic energy. That concludes our lesson for today. If you like this topics we covered, give it a like, subscribe if you haven't done so already, and I'll see you next time.